Okay, so what is happening today is the first of a series of lectures that we've organized for you over the summer. It's an opportunity for us to, I think, get across a lot of different topics, ideas, right? Just plant them in your heads, right? So that as you go forward, some, I don't know, bell might ring at some point, right? You might want to follow up. So maybe, I don't know, 10-ish lectures over the next 8 weeks. Maybe around times like this. How should you be interpreting them? Don't think of this as a course and we're going to ask you questions and there's going to be an exam and so on. Think of it more as an opportunity to learn a variety of topics. Okay, so broadly the buckets into which these things will fall: AI, which is kind of where I come from, robotics, computer science in general. Okay, so online learning is usually not the first topic that is covered, let's say in a course on machine learning. It comes a little bit downstream. The reason I'm doing it is it's self-contained, doesn't need too much background, and I think the thing that it gets across, which I really is what I want to get across to you, is the important significance of mathematics. Okay, so I think a lot of you, by default, I'm assuming, or you try to, I don't know, put things together, work with your hands, do hardware, embedded systems, a lot of maybe empirical validation of the systems that you build, which is great, okay? But there is also this complementary side, particularly to do with AI decision making, where a lot of progress has been made, right, and will be made using mathematical concepts. Now is the time. You're still in college, you're young, right? It's an opportunity for you to really brush up on these skills, look at this world of mathematics as a way of analyzing systems, designing algorithms, and so on. I'm hoping that today's talk will give you that opportunity, okay? It's called online learning, okay? Just when we met the other day, I said it's a good idea for people to be meeting in person, don't do things online. And then here I am, right? And the first lecture is called online learning. Am I being a hypocrite? Okay, this is not online versus in person. This is online as the opposite of offline. Okay, so technically, what does it mean to be doing something online? Not in the sense of going on the internet and doing something, but as an algorithm or as a process, what is online as opposed to offline? Yeah, I've told you you're supposed to ask questions or answer questions also. To say something. Yeah. Computing in the cloud instead of doing it on device, that is like the system's sort of definition of online versus offline. But more in the algorithms, AI setup, it has a different meaning. What is that? On the go, okay, updating on the go. So if you've seen traditional machine learning, what are you usually given? You're given a data set, okay? You're given, here are inputs and here are the corresponding outputs, and then you learn from that, right? So that's like the sort of offline training regime where you learn, whatever you learn, you go and a bank gathers a lot of data, does the learning. It now has a predictor which, if somebody comes to apply for a bank loan, they'll use a predictor and say sanction, not sanction, okay? So the offline learning is done and it is used. Online learning is a thing where to begin you don't know anything. Nothing is given to you. It is as you go through life, right? Time step 1, 2, 3, 4 that you start getting some observations about the world and you have to, I don't know, learn from that and also update your behavior as you go along. Okay, this is a very natural paradigm in agentic, like robotic kind of setups where there's an agent literally that gets born in the world and it has to negotiate life, right? So it doesn't have too much told to it beforehand, but it encounters the world and learns from that. So it is online learning in that sense, okay? All right, so we're going to get started with this topic using a sort of fun exercise, okay? Here is what it is. So imagine that I have with me 3 coins, okay? They have very interesting names, coin 1, 2, and 3, okay? Those are the names of these 3 coins. Coin 1 has a probability P1 of showing up heads when you toss it, okay? So mostly, right, the coins that we encounter, we assume that with probability half you'll get head, with the other half probability you'll get tail, right? But you could also have a coin which with probability 0.9 gives you a head, right? So P1 could be 0.9 or 0.6 or any probability, any number between 0 and 1. For coin 2, that head probability is P2. For coin 3, it is P3. Okay? And what is the game? One of you has to play the game, or all of you can play the game. But those playing the game do not know what P1, P2, and P3 are. Okay? They're there. Okay? That is the reality, but that is not given to you. However, you are expected to do the following. You are given a total of 20 tosses. Okay? So what you can do is, you can pick any one coin, right? Toss it. If you toss it, I will tell you after tossing it whether it showed up head or tail. If you had tossed coin 2, indeed the probability with which I will say head is P2 and the probability with which I will say tail is 1 minus P2. Okay? Similarly for coin 1 and coin 3. And what is your aim at the end of this? 20 tosses, you're supposed to maximize the number of heads. Okay? That's the exercise. What I'm going to need is somebody to volunteer to play the game. So here's how it goes. Abhinav, whatever you say, right, I will act according to your instruction, but the entire crowd here is at liberty to influence Abhinav. You can raise your voice and tell him do this, do that, right, or disagree with him. I have a small program. You'll have to believe me that whatever the program's doing is consistent with what I said. Okay, so this is my, I don't know, rudimentary interface. There's 3 coins. None of them have been tossed yet. 20 tosses are left. You have to say 1, 2, or 3.
Okay.
What do you say?
1.
1. Coin 1 gave a head.
He gave head.
Right on.
Okay. Coin.
Applause is good. Right. Yeah.
Coin 1 again.
Coin 1 again. That's
Okay.
a tail. Okay. Don't blame it on Abhinav. Give him the credit for the successes, but not for failures. Okay. You have a head and a tail. Okay, from coin 1.
Every
Okay,
time
let's just do a few more. Let's go to 5
Okay.
and then we'll take stock and decide what to do. What do we toss now?
Coin 2.
Coin 2. Okay. Coin 2 gets tossed and gives you a tail.
Okay. Coin 3. Coin 3.
3. All right. Head. Okay, you're
Yeah,
saying
coin
coin 3 because you're
Yeah.
optimistic that maybe coin 3 is a 0.999 probability coin.
So coin 3.
Coin 3 again. Okay. 3 is the real deal. 3 again.
Yeah. Okay.
Okay, we are at 7 tosses. That's about 1/3. So I think Abhinav has done his job. Any other volunteers?
Coin 3 next.
Coin 3. Somebody agree with him? Nobody feels sorry for coin 1? You're supposed to have a heart in addition to a brain. Coin 3, okay. I can show you the program that's generating it, okay. It's a piece of code, kind of thing that you could write. Yes, Devanshu.
Coin 3.
3 again.
Yes.
3 is your lucky number. Okay, somebody doesn't want 3, you have to speak up.
See, based on the probabilities, coin 3 has higher chance.
But we have not given enough chance for other two.
See, coin 1 has given 2 chance and half probability is there. Coin 3 has 3/5 probability.
Because it has 5, it is 3. So maybe the other 3 outcomes of coin would be different.
Yeah, but we don't know that, right? We only know the current probabilities. So based on that, I think we should.
All right, quick.
See, coin 1 has half probability and coin 3 has 3/5 and coin 2 has 0.
He just said something. Hold on. You said coin 1 has a half probability. Coin 2 has what?
0.
And coin 3?
3/5.
So what are these numbers? I mean, he's raised something. Is this the probability with which coin 1 is generating heads?
No,
Okay, but then what is it?
it is kind of a greedy approach in which I am just calculating what is the
You're
current
doing
probability.
something right, but this kind of has a name. Okay, so this is not coming from the truth. It's coming from the
Observation.
evidence. Okay, whatever outcomes got generated. It turns out that this is actually a good estimate of the truth. Okay, it's not the truth, but based on the data, we have to kind of think about what might be the real probability, right? So this is actually called the maximum likelihood estimate. But call it whatever you want, okay? Yeah, so go on.
Maybe give it coin 3 a chance again.
You want more and more chance for coin 3.
Now,
Nobody believes that coin 2 could coin 2 be the coin with the highest probability?
yeah,
It just got unlucky first time, right?
let's give another chance to coin 2.
2.
Yeah.
Okay. Coin 2 gave a head. Coin 3.
Yeah. Okay.
Okay, at this point, is there anything to distinguish coin 1 and coin 2?
No.
They have the same number of heads and tails. Do you think, I mean, if you're watching IPL, right, somebody who scored a century in the previous match, they're supposed to carry momentum with them and score a 50 in the next match. You think that will happen with these coins? No. Yes? No? It won't happen, okay? The process is you're generating outcomes independently on each toss, okay? You don't remember anything when you're tossing the coin. Okay, so 1, 2 or 3?
2.
2, okay.
Let's proceed with 3.
3, okay.
3. Half and 3.
3 again.
Yes.
Okay, all right. So how many heads do you have at this point? Total? 8.
8.
8 out of 14, I think. Okay. Anyway, so 6 to go. I think it's taking a little bit of time. So shall I fill it in?
Yes.
Or anybody else? Quickly, right? Yeah. Is it a good idea to look at the data at each time step and decide what to do, or just decide upfront and do it? What is this called in robotics? Dash, exactly, right? Open loop and closed loop control, okay? So you can always do better with closed loop control. It takes more, I don't know, thinking time or whatever it is, but sort of in an information theoretic sense, right? You're making use of all the information. So maybe I'll do 3, 2 to go. Okay, I'm just going with 3s, okay? Okay, so total heads is 11, well played to the class. What are you very curious to know right now? You want to know what the generating probabilities were. What are your best estimates of those probabilities? What we had written, right? Similarly, you would kind of, if you have to put one number, you'll probably say this is half, this is 1/3, and this is whatever, right? Number of heads divided by total number of tosses. Those are not the actual probabilities, but that's what we estimate. 2, 2, 2, 2, 2. 3, 3, 3, 3, 3. Okay? There's a tie.
Yeah,
You don't like the real world, do you?
obviously coin 3 then.
Sorry?
Coin 3, yeah.
3.
Yeah.
You remember from last time. You're not supposed to use last time's data, right? If this is an independent trial. Yeah. The biases stay the same. Okay, the probability is, okay, anyway. 3 again.
3 again, 3 like continuously 3.
That's not consistent with your philosophy, is it?
My philosophy was
3
divide.
has a lower empirical average compared to 2 now. Okay, I'm going to go with 2, 1. Okay, I don't mind. Doesn't matter really. Okay, so let's do 1, 2, and 1, 3. 9. Okay. Anyway, not a big deal. So let me show you what the probabilities were. 0.3, 0.4, and 0.6.
Makes
Okay,
sense.
so P1 was 0.3, P2 was 0.4, P3 was 0.6. So which coin was the most profitable coin?
3.
Which I think in both cases the one you ended up tossing the most, but I think the distributions were a little bit different. This is an example of online learning. Okay, in what sense? There are these 3 coins, right? They have their probabilities which we don't know, but as we go, right, we're getting data about them. Based on the data, we're deciding what to do, and we have some objective function in terms of what we want to achieve. Over a lifetime of 20, we want to get the maximum number of heads. Okay, this was challenging because we didn't know P1, P2, P3. If you knew P1, P2, P3, if I tell you to play the game now, what will you do? Sorry? Coin 3 all the time. Even if it gives you like 5 tails at the beginning? Yes, no? Okay, right? So this is clarity that you should have. The future, I have told you, right? I'm sort of giving it to you in writing that it doesn't depend on the past, okay? Every time, independently, forgetting everything else, when you toss a coin, the P1, P, whatever you'll get a head, 1 minus P, whatever you'll get a tail, okay? So even if you've got 5 tails, but you know that P3 is the highest, you should always toss P3 to maximize the expected number of heads that you will get. We sort of saw this in the form of a game, right? But why are people interested in this? This is a technology that is actually very prevalent, okay? You would have probably encountered it in many places without knowing it is happening. So imagine that you're on a particular page and you're seeing a banner ad, okay? Banner ad is like a, I don't know, there's some real estate for showing ads, right? Now, maybe the advertiser has 3 different styles or templates for rendering their ad. Okay, the same ad they can show you with capital letters for the title, right, or blue font or yellow background, okay. Designers came up with these. Now, in most of these cases, it is in the web page's interest to show you an ad that will engage you, as measured either in the form of you clicking it or in the form of you clicking and then going and buying something, okay. So simplistically, if we say what we would like to do is to show that template which has the highest probability of being clicked, okay. It's the same problem that you solved right now, okay. These 3 ads have 3 different probabilities of people clicking them, right? We should be showing the one which has the highest probability of click. We don't know what that is. So what would these advertising companies do? Play the game that you played, okay? They try each a few times, which means they are exploring, okay? As they get data, they become a little bit more confident about one of these having a higher probability than the others. You get some estimates like this of the probabilities. You use that to guide your future decision making. You go ahead and exploit, okay. Recommender systems, when you're reading the news, right, maybe your site tracks you and knows that most of the time you're going to be reading something about science, but who knows, you might be a history buff. They've not shown you any history articles so far. They will explore once in a while and show you something in history. If you click that, right, they figure out that actually history might also be something that you like. So getting this balance right between exploring and exploiting, this is one place where it happens. One of the oldest applications of this explore-exploit trade-off is with doctors treating patients. Okay, so imagine that a dermatologist has 3 different creams that they can prescribe for a particular skin condition. They don't know which one has the highest chance of succeeding, efficacy on the patient. So they start giving different creams to different patients. As the data comes back, they give more and more volume, right, to the cream that seems to be working more successfully. Imagine you have a computer network, okay, whatever, there is nodes talking to each other, right? And so maybe a packet comes in, okay, and then this node has to decide, do I send it out on this or on this or on this, okay? At the lowest sort of level, right, there would be errors in transmission, okay? To get a packet across to its destination, you might have to send it multiple times. You should ideally be sending it on the channel with the smallest amount of error, okay? But do you know these error rates? You will know it only by sending packets and seeing whether they go or not, okay? So by doing, you understand about the system, but then at the same time, you have to optimize for your objective function, okay? So again, communication channels, including phone, right? The way your phone talks to the tower and so on, there are these kind of problems. Reinforcement learning, this is a very basic element of reinforcement learning, okay? Which we'll probably look at later in one of the presentations. For example, game playing agents. How many of you have heard of a program that about 10 years back beat a human being in the game of Go? What was the name of that program? AlphaGo, okay? It was built by a company called DeepMind. I think subsequently it became Google DeepMind or just before. Okay, but game playing programs, agents, internally, right, when they are deciding what to do, they use this kind of explore exploit, okay? So it's a general idea which has wide applicability. Okay, so what is the plan? I have told you this in terms of game and so on, but I think we've already gotten across the main concept. The plan is to follow this up with much more like clarity in terms of defining the problem, mathematically stating what is it we want to do, coming up with algorithms which will do it. All of that, right, I'm hoping to do in the next hour. So this is what I meant by using mathematics to our advantage, okay? So formally, this kind of a setup is called a stochastic multi-armed bandit, okay? So what is a stochastic multi-armed bandit? Here's a picture of an 8-armed bandit. Each of these, think of it as an arm of the bandit. This is the real line going from 0 to 1. This is one arm of the bandit, and each arm is associated with what we call a Bernoulli distribution. Okay, a Bernoulli distribution is a probability distribution that takes two values. Okay, it'll either give you a 0 or a 1. It gives you a 1 with some probability, so that's the probability that I have shown here as a blue line. The remaining probability you'll get a 0. So for example, this arm of the bandit, if you pull it, so pulling an arm is just terminology, it's the same thing as tossing a coin. Okay, with this probability, okay, this probability, let's say this is 0.85 or something like that, you will get a 1. With this probability, you will get a 0. Think of 1 as head and 0 as tail. Okay, and each of these arms has its own underlying Bernoulli distribution, which is defined by one number, okay, the mean, okay, which is also the probability of getting a 1. Arm A has mean PA, okay. PA is the mathematical quantity we use to denote the mean. Think of these as rewards, okay. So mean reward is simply like PA times 1 plus 1 minus PA times 0, right? This, it takes two values. So you can forget the 0 thing, and the mean is going to be PA. Okay, and the highest of these is called P star. Okay, P star is the highest possible mean. Okay, so this is called a bandit. Why is called a bandit? That's because of this history. So back in the day, I don't know, it might still be there in casinos in Las Vegas and so on, right? You could go and do some gambling. There was this machine called a one-arm bandit. Okay, you get some reward. Okay, and that reward will come to you probabilistically, much like what we're doing with our coins. Okay, you toss it with some probability, you'll get a 1, which is your reward, and remaining probability you don't get a reward. If you have multiple of these next to each other, that becomes a multi-armed bandit. Having defined a bandit, now let's do the more critical thing we have to do, which is to define how we interact with the bandit, right? What is it that we are trying to do, okay, given the bandit? So what we are trying to do is described by what an algorithm tries to do. Okay, so you can think of yourself as an algorithm that was recently interacting with this bandit. We could also write code, right? Whatever you're doing, what were you doing? You're looking at the data and deciding which coin to toss next, right? So could an algorithm. Okay, this is basically what AI and machine learning is doing today. The kind of things that maybe we see and we drive, right? A self-driving car sees with its vision and its LiDAR, and it gives control signals to the steering and the acceleration and so on, right? So similarly, this is an agent which looks at the outcomes so far and decides what to do. The what to do here being deciding which arm to pull next. Is available to the algorithm to inform its decision making is whatever has happened in the past. So what has happened in the past? At time step 1, we pulled some arm, call that A1. We got a reward, either a 0 or a 1, call that R1. Based on that, next time step, we pulled arm A2, we got a reward R2, and this has happened T minus 1 times. Okay, this is all we can see. This is the data, and we have this for all the arms. Okay, all the arms that we pulled, we know at what point we pulled them, what data we got, what reward we got for it, and so on. Now, based on that, the algorithm has to determine the arm to pull at the next time step. Okay, it has to decide AT. That's the job of the algorithm. Okay, and if it does that, then the world, okay, or the bandit or the environment, whatever we want to call it, comes back to the agent and says, okay, you pulled arm AT, you're going to get reward RT. And what we know is that RT is going to be 1 with probability, whatever was A's probability, right? The underlying Bernoulli had a mean parameter. That is the probability with which you will get 1 for pulling arm AT. 1 minus of that is the probability with which you will get a tail. Okay? So far so good. You look at the data, your job or an algorithm's job is to decide what to do. Once you do it, right, once you pull it, laws of physics maybe or a computer program, right, does some randomness and it comes back, tells you what the outcome was. Okay, and then you repeat. Capital T here is sometimes called the horizon. Okay, it's the number of time steps for which the agent lives, or it can be called the sampling budget. It's got different names. Now fill in this blank. Okay, the maximum expected reward, okay, that is possible in T pulls. If you're pulling capital T times, in expectation, what is the maximum accumulated reward that you can get? Okay, what is the maximum reward that you can get? No expectation. If you have T pulls, right? So you can just keep getting head T times. Okay, so capital T is the maximum possible reward. But in expectation, what does that mean? It means you fix your algorithm. Okay, you fix the program that is going to play. You play that same program lots and lots of times and see on average how much is it getting. Could that algorithm on average get T as reward? It's also going to get unlucky sometime, right? So in expectation, what is the most that it can get? Sorry? T times P star. Okay, so the most that you can get on any time step in expectation is P star. Okay, if you're always tossing the optimal coin or pulling the best arm, you're going to get P star. So an algorithm that in fact always pulls the optimal arm, okay, doesn't look at the data of all the other arms, it just decides I'm going to keep pulling arm 3. If P3 is P star, then that algorithm in expectation is going to get T times P star. How many of you understand this somewhat? Not confidently enough to raise your hands. Okay, so this is the reason I'm doing it. Okay, this is like very basic probability. Do a course on probability, right? You should become very familiar with reasoning like this because it's an excellent model of how the world behaves. Okay, I don't know, you're watching IPL, right? You want to know like which team has a higher chance of winning. These things don't happen deterministically, right? There are probabilities with so many different confounding variables. How you still want to reason about them, right? So probability theory helps you, and this is elementary probability, okay? Expectations and so on. Okay, so the maximum expected reward possible is T times P star. On the other hand, the actual expected reward for an algorithm, what is that? That is simply summing up over all the time steps, the expected reward for each time step. So if you fix an algorithm, in expectation, it will get something at time step 1, time step 2, time step 3. You sum all of those things up, that is actually what an algorithm is going to get. Is that going to be T times P star? For a reasonable algorithm, it's not going to be. For a very weird algorithm that somehow magically always pulls the optimal arm, it's going to be T times P star. But such an algorithm might not do very well on problems where the arm that it's pulling is not an optimal arm, right? So if an algorithm is actually trying to balance, learn, do something, it's not going to get T times P star. What is called the regret of the algorithm is the difference between these two quantities, okay? So best you can get is T times P star. What you actually get is this sum over here. So this difference between the best achievable and what you actually achieve is called your regret. Okay, regret comes from maybe the sense that if you knew what the reality was, what would you have done? You didn't know it, right? Therefore, you end up with something else. That's your amount of regret. Okay, it's denoted RT. It depends on the horizon. What would we like? Would we like to design an algorithm that has a high regret or a low regret? High rewards and therefore low regret, because reward is going in as negative. Okay, so we desire an algorithm that minimizes regret. Okay, so what I'm going to do is have like two sections of this talk. First, introducing you to a very simple, easy to understand family of algorithms called epsilon greedy algorithms. Having done that, we'll see that they have some limitations, and we'll look at something a little bit more sophisticated. Sophisticated doesn't mean complex, it's somewhat simple, but which tend to work better. So here is the deal with epsilon greedy algorithms. They have this one parameter called epsilon. Okay, so epsilon is number between 0 and 1. And what epsilon determines in these algorithms is the extent to which they will explode. Okay, by setting epsilon differently, you will promote different amount of exploration. So we'll see exactly what that means. To initialize, so I'm going to give you 3 different variations of the same thing. Let's call them epsilon greedy 1, 2, and 3. So we'll, I'll sort of put them down in sequence. But assume for each of these algorithms, the way we initialize these algorithms is we pull each arm once. Okay, if you pull each arm once, it has a well-defined empirical mean. Okay, so for any arm, the empirical mean is like number of heads divided by total number of pulls. Okay, or if head is taken as a reward of 1, total reward divided by total pulls. This thing is called the empirical Okay, all right. So what is epsilon greedy 1? Okay, here is the first cut for epsilon greedy. So let's assume that we know the horizon capital T. So what epsilon greedy 1 is going to do is up to epsilon capital T steps. Okay, so let's say capital T is 1000 and epsilon is 0.1. That means for the first 100 steps, it is going to sample arms uniformly at random. Okay, so at every time step, it will pick one of these three with equal probability. Do this till you've reached 100 steps. Once you've reached 100 steps, you see which arm has the highest empirical average. Okay, you get the data for each arm, you see which one has the highest empirical mean, call that arm A best. Okay, and then what you do for remaining pulls 101 through 1000, pull A best. Okay, so we explored for the first epsilon T steps, identified empirically what was the best arm, and then we exploited in the sense that we just stuck with that choice, right, without pulling the other arms again. Do you think it's a good algorithm? No, because I already told you there's more algorithms to come. Is it a reasonable algorithm? Is this kind of what you were also doing, right? We were exploring a little bit, looking at the data, and then we had only 20 tosses, so you also want to exploit, okay? So what do you think will be the effect of epsilon on this? What will happen if you make epsilon large? If we make epsilon, let's say 0.8. Is 0.8 a good choice? No, 0.8 here means, suppose we have 1000 pulls. For 800 pulls, we are going to be pulling uniformly at random. And then for remaining 200, we will pull the best one. 0.8 might be too much because you are exploring too much. What about 0.0001? Something like that. Too less because you're not exploring enough. Okay, let's say I just tossed each coin 2 times. One gave me 2 heads, the others gave me 1 head, and then I'm only going to toss the coin that gave me 2 heads, right? It might just be the others were a little unlucky, right? The first couple of pulls were not very good for them. So we want to explore a little bit more. So you should expect that as epsilon is varied, right, there is some kind of sweet spot. Very small is not good, very large is also not good, okay? So this is exactly what will happen on the forthcoming slide, right? I will, actually, before I show you this, right, I'll actually show you some empirical results consistent with that sort of expectation that we will have. Okay, but now just looking at this, can you propose like a simple switch which should do better? If you look at this, what is it doing that is a little bit unsatisfactory? So imagine that after epsilon T pulls, we identified this arm A best, and then what are we going to do? We're going to keep sampling that arm A best, right? While you're doing that, what if A best's empirical average falls below other arms, right, which we had explored in the first epsilon T steps? Would you still continue with A best? Right? You might as well switch to the one that at any point of time has the highest empirical average, right? So that simple change is what I'm going to call epsilon greedy 2. Okay, so for the first epsilon T steps, pull arms uniformly at random. Beyond that, at any point of time, you see which arm has the highest empirical average, pull that one. Okay, chances are it might just be that A best we identified, or it could potentially change, right, in the second phase of the algorithm. For any fixed value of epsilon, do you expect epsilon greedy 1 to do better or epsilon greedy 2 to do better? Okay, this much I think our intuition I think will get validated when we look at the results. Now epsilon greedy 3 is what in the literature a lot of people usually typically call epsilon greedy. Okay, unlike the first 2 algorithms, this is a randomized algorithm. Okay, so what does it do? At every time step, okay, literally at every time step, it explores with probability epsilon and it exploits with probability 1 minus epsilon. If you look at epsilon greedy 1 and epsilon greedy 2, so suppose this is your capital T, up to epsilon T, right, they're basically doing explore, roughly speaking, crudely speaking, okay, and beyond this they're doing exploit. What epsilon greedy 3 does is literally at every time step, with some probability epsilon, it will explore, and with the remaining probability 1 minus epsilon, it will exploit. What does that mean? With probability epsilon, sample an arm uniformly at random, with the remaining probability, sample an arm with the highest empirical average. So at every point of time, you see which arm has the highest empirical average. Are we going to pull that arm? With probability 1 minus epsilon, we'll pull that arm, but with some small probability, we'll pull an arm chosen uniformly at random. So you're still mixing, exploring, exploiting, but you're doing this at every time step, okay? Not sort of doing it by splitting the horizon. Okay, so here are these three algorithms. Do you think epsilon greedy 3 will perform better or worse than epsilon greedy 1? Better. Okay, so frankly, I don't remember. The only thing I think we should expect is that 2 is better than 1. Otherwise, there might not be too much to say very conclusively. So I have actually implemented these three algorithms on a bandit that had 20 arms. Okay, the mean rewards of these arms were actually in arithmetic progression 0.01, 0.02 through 0.2. Okay, these are the true means, okay, which the algorithm doesn't know, but that's how I have run it. This is the same thing as the coins biases that I showed you, right? And I'm running it for a horizon of 100,000. Okay, what do we see? So this is what we see. Okay, so what's being plotted here on the x-axis is different values of epsilon from 0.01 or 0.005 through basically 0.1. On the y-axis is regret. Okay, so if you run epsilon greedy 1 with epsilon being 0.05 for a horizon of 100,000 on this bandit instance, the regret that you will get is about 1500 or something like that. Okay, so you can see here's how it is varying. You can see literally for all three of these algorithms that small, very small epsilon is not good. Okay, you're not exploring enough. As you make epsilon larger, again the regret is going up. Okay, because you're exploring too much. So some intermediate value is the best one, and if you indeed compare epsilon greedy 1 and 2, which is blue and black, you can see that in fact epsilon greedy 2 seems to be the best across the entire range. Okay. Okay, so if we have to pick one representative from this family of epsilon greedy algorithms based on what we have done, okay, that should be epsilon greedy 2, and in fact it is epsilon greedy 2 with epsilon being 0.03, this point over here. This version of epsilon greedy algorithms, okay, implemented as epsilon greedy 3 with epsilon being 0.03, I'm going to call epsilon greedy star, okay, because I'm now going to compare epsilon greedy with some other algorithms. I'm taking the best representative from this family, okay, from what we've seen, that is epsilon greedy 2 with epsilon being 0.03, and that has a regret of 822. Okay, plus or minus some standard error over this horizon. Okay, that's epsilon greedy.
The same algorithm might give different results for like
For a different bandit instance.
Yeah, might be one algorithm might be better than the other for one problem statement, and it might differ for the other.
Well said. That's
So-
absolutely true. So this choice of epsilon greedy star as a representative is only for this bandit instance I1 and this horizon. Even for the same, when I say bandit instance, I'm fixing all those means and so on, okay? Can you think of something, some way in which they're not really being very smart? There's something a little bit silly that they're doing. Arm 1, arm 2, arm 3, the number of heads and tails for this. So suppose clearly this is the best arm, okay? So it got 800 heads and 200 tails, okay? This one here got, let's say, 300 and 200. Okay, so the empirical mean here is 0.8. It is 0.6. Okay, and this one is 100 out of 300. 100 out of 400, yeah. So this is going to be 0.25, right? Is my calculation correct? 800 divided by 1000, 0.8. 300 divided by 500, 0.6. 100 divided by 400 is 0.27. Okay. Now what would epsilon greedy do, right? When the data looks like this, with probability 1 minus epsilon, which one will it pick? It would exploit and therefore pick which one? This one, the first one. What is the probability with which it will pick this and this? Right, so the probability of pulling, this is going to be 1 minus epsilon, in fact plus epsilon divided by 3. Okay, it's going to get the exploration probability, but also 1/3 of the it's going to get an exploitation probability, 1/3 of the exploration probability. This will get epsilon divided by 3, this will get epsilon divided by 3. So what Yashwant has noticed is we are giving the same exploration probability to both of these arms, where this is actually a 0.6 from 500 pulls, this is a 0.25 from 400 pulls. Okay, you would rather give which of these a little bit more probability? The second one, right? So instead of epsilon 3, maybe you can give this, I don't know, some other number like how much is 0.33, right? So make this 0.25 epsilon, make this 0.5 epsilon, make this 0.16 epsilon, maybe something like that, right? This would be a little bit more responding to the fact that these have different rewards, but epsilon 3 is not doing that. What we should expect is that an algorithm that's even more, I don't know, smart about the way it proceeds would do something like this. Okay, and the algorithms that are coming up will indeed do it. Okay, and they'll do it. This is why we need the mathematics. Okay, well, actually, what probabilities will you put on these things? It has to come from somewhere, right? Where does it come from? It comes from mathematical analysis. Okay, here are two improved algorithms. One is from about, in fact, these are both fairly old algorithms. Okay, so the first one is called UCB. Okay, upper confidence bounds based algorithm. People just call the algorithm itself UCB. Now let me tell you what UCB does. So just to get initialized, we just pull each arm once. Okay, so that's not the interesting part. The real heart of the algorithm is the following. At every time t, for each arm A, we define this quantity called the UCB of the arm. Okay, UCB of arm A at time t. Now what is that UCB? That UCB is the sum of two terms. The first term, okay, P hat TA, is basically the empirical mean of the arm, okay, at time step t. Okay, that's one quantity. But then there's a second quantity. Now that quantity is sometimes called the exploration bonus. Okay, and what is that? That happens to be the square root of 2 times log t divided by UTA. Okay, now you might wonder where that comes from. If you dwell enough on this, right, you'll understand like why this particular formula is used. But intuitively, right, what is happening, we will understand when we see how the algorithm itself works. Okay, so what are we doing? At every time step for every arm, we are computing this quantity called the UCB, which is the sum of the empirical mean and the exploration bonus. The denominator term in the exploration bonus here, UTA, is the number of times that the arm has been pulled up to that point. Okay, so here, for example, is a picture I have drawn. So for each arm, this brown line, let's say that's the empirical mean, and this black region, that's the exploration bonus. Okay, so if you sum them up, that's the UCB. Okay, so this is the UCB for the first arm, this is UCB for the second arm, UCB for the third arm, and so on. So what do you notice about this exploration bonus? Suppose an arm has been pulled lots and lots of times. Will it have a large exploration bonus or a small exploration bonus? Why small? Because U is large and U comes in the denominator here. So 1 over U is going to be small. So you're adding something very small. Okay, if it's very, very large, exploration bonus is very small. Basically, the UCB is pretty much the empirical mean. But if an arm has not been sampled, right, if its U is small, then the exploration bonus is large. Okay, and therefore the UCB is also large. Okay, that's like intuitively what's going on here. Now, what is the algorithm itself? The algorithm says, you have all of this data, you've drawn all of these UCBs, which arm are you going to pull? You pull that arm that has the highest UCB. Okay, so if you see this picture here, which arm has the highest UCB? This arm here. Okay, does this arm have the highest empirical mean? No, okay, because there's at least 2 more arms that have higher empirical means, but it has the highest combination of empirical mean and exploration bonus. Okay, so that's the arm that gets pulled. So what is the philosophy here? We want to give arms credit for having a high empirical mean, but we also want to explore enough. If an arm has a low empirical mean, but it's not been pulled enough, you want to give it some bonus. Okay, that is being done by defining this one formula, which is the UCB. Questions about the algorithm?
What if that approach backfires, right? So if I have a certain success rate with one arm,
yeah.
right? So if I have a certain probability that is lower than all of the other arms, but I have not pulled it enough to know, right? What if in the upcoming trials, the arm does not give the result that I wanted to give?
You're going to do it only once, right? So after you do this, as soon as you do this, so once you pull this arm, you're going to get data point for this arm, which will be either a 0 or a 1 reward. What's going to happen based on that? The empirical mean of that arm will change, and T goes up by 1 for all the arms, right? So for this arm, the UCB will come down by a little bit because the empirical mean comes down by a little bit. But for all the other arms, the UCB goes up by a little bit because their empirical means stay the same, but the exploration bonus goes up by just a little bit.
Understood.
Right?
Okay.
So yes, it might be wasteful, but you have to draw this trade-off. What if maybe it was a good arm and you did not give it enough trial, right? Okay, so the good thing about UCB is that it is optimal in a particular sense, okay? So mathematically it has been worked out that any bandit algorithm that sort of works well on all instances has to incur a regret that grows at least logarithmically with the horizon. Okay, so if t is your horizon, you cannot do better than some constant times log t. Okay, there's no algorithm like that. There's a mathematical proof, right, that people came up with in 1985 saying that, I mean, how many of you know about an algorithm called sorting in computer science? What is sorting? You're given a bunch of numbers, okay, n numbers, you have to arrange them in ascending order, okay. How many operations does this take as a function of n? Do you know? This is what people analyze in algorithms class. What is that? Time comp, but what is it as a function of n for sorting? It is in the order of n log n, okay. There are algorithms that do achieve n log n. There is also proof that no algorithm that works correctly on all problem instances can do better than n log n. There cannot be an algorithm that does square root of n log n, right, or n log n. It's not possible. Okay, there's a mathematical proof. So this is again where mathematics comes into the picture to tell us what is, right, at all possible. So it is known in the context of bandits that no algorithm can achieve better than log t regret on all instances. UCB is an algorithm that actually achieves it. Okay, so this lecture that I'm doing, right, is something that I do as the second or third lecture in my class. I teach a course on reinforcement learning. In that course, we actually do the proof. Okay, it's like a full session where mathematically 1, 2, 3 we write down all the steps, which ideas from probability we are using, and so on. You would like agents to be rational, right? So if you're designing algorithms, we would like some assurance on whether they are the best that we can do. So UCB is indeed the best that you can do up to a constant factor. Okay, so on a given problem instance, UCB achieves some constant times log t. There's been a slight variant of UCB called KL UCB. Too much for this lecture, but KL UCB also keeps this log t dependence, but it improves the constant. It is something like on the same problem instance, UCB will give you 25 times log t. This one might give you 8 times log t. Okay, and the lower bound tells you that you can only do 8 times log t. Okay, in that sense, KL UCB is actually an optimal algorithm that you cannot do better than. This is borne out in our empirical experiment. Okay, when we implement these algorithms on the same I1 bandit instance that I showed you some time back, the regret of UCB is 1168. For KL UCB, it is 738. So it looks like UCB is actually giving us a little bit higher than epsilon greedy, which is okay. Okay, but KL UCB is giving us a smaller regret. We'll understand this a little bit downstream. All right, now let's look at yet another family of algorithms, actually one algorithm called Thompson sampling. But to understand Thompson sampling, you need to understand a little bit about a probability distribution called the beta distribution. How many of you have heard of Gaussian distribution? Gaussian distribution is sometimes called the normal distribution, right? So you have data, there's a random variable, okay? There's a real valued random variable that takes values basically from minus infinity to infinity. It can take any value, okay? But what's the probability with which it will take some value? Okay, so that is what the PDF of the Gaussian distribution, okay, I'm not very good at drawing, but this is roughly the way a Gaussian distribution looks, which has this as its, okay, okay, let's call it mean. And there is a quantity that sort of shows up somewhere here, which is called the standard deviation, okay. So basically, I don't remember the number, maybe 67% of the samples that you get from a Gaussian will lie in this region, some 99 will lie in this region, and so on, okay. This is a continuous random variable, so this is called a probability density function. How many of you have actually done a course in probability? Smaller number, okay. Is that because the others are second year student and you do it in your third year or something like that? Or maybe your subject does not have probability? Next semester. How many of you are going through an engineering degree without doing probability? It's possible, right? Just raise your hand. I'm curious to know. All of you are doing it? Okay, so basic probability, I would strongly encourage you to do it. You can see, right, in designing solutions for things like this, it comes very handy. Okay, this is not very complex stuff. It's relatively basic, but you need to get the hang of it. Okay. Okay, so this is a Gaussian distribution. Just like there's a Gaussian distribution, there is this thing called the beta distribution. Okay, so that is what I am defining here. The Gaussian random variable takes values from minus infinity to infinity. In fact, I think I have drawn it here. Okay, so here's a Gaussian, the purple or something like that curve, right, is the PDF when the mean is 0. Here is yet another curve with a mean of 5, okay, standard deviation of 1. Okay, these are all Gaussians. There is something similar called a beta distribution, which takes values only between 0 and 1. Okay, the random variable, the support of the beta distribution is only 0 to 1. Okay, the shape of this beta distribution is determined by two parameters. Just like Gaussian has mean and variance, beta distribution has these two parameters called alpha and beta. Okay, so just like you say, this will be called n mu sigma squared or something like this, right? So similarly, you have a beta distribution with parameters alpha and beta. Turns out that the mean of the beta distribution will be alpha divided by alpha plus beta. The variance will be something else, okay? But basically, this is how it looks, okay? An a beta distribution for which both parameters are 1 is basically the uniform distribution, okay? As you have different values of alpha and beta, beta 3, 4 looks like this. Beta 5, 15 has a smaller variance, it looks like this, the PDF looks like this, and so on. Okay, so what does this mean? It means when you draw samples from this beta distribution, for example with this peaked curve, most of your samples, right, will be somewhere over here. Okay, and fewer samples you will get, right, with values beyond 0.6 and so on. Do you know what it means to sample from a distribution? No. Okay, let me actually show you this then. Let's go with this blue distribution. Okay, so this blue one has alpha of 5 and beta of 15. My claim is when you sample from that distribution, you should get a value that is sort of between 0.05 and 0.4 or something like that. Okay, you will get more and more like this, fewer and fewer in larger ranges. So let's see if that happens. Okay, I got 0.19. Is that what I was saying? Yeah, okay. I'll do it again. Will I get the same answer again? It's a random sample. Each time you'll get something different. Okay, 0.21, 0.28, 0.19, 0.35, 0.28, 0.30. Okay, this is what these are all. Each of these is a sample from a beta distribution whose parameters are 5 and 15. Okay, you can do the same thing with Gaussian and uniform distribution and so on. Okay. All right. Now, what is the connection between beta distribution and this next algorithm, which is called Thompson sampling? We are going to design an algorithm for our bandit, right? Somehow using this beta distribution internally. Exactly how? Okay, so Thompson sampling is an algorithm that was introduced by somebody called Thomson in 1933. So imagine this algorithm is almost 100 years old. Okay, again, right? It's fairly simple algorithm to describe. So at time t, let arm A have STA successes. Success is the same as one reward, okay, or heads. And FTA failures, okay. F stands for failure, which is the same as getting a zero reward or a tail. Earlier we were saying empirical mean and number of pulls. Equivalently, we can remember the number of times you got a 1 and the number of times you got a 0. Okay, that's called the successes and failures. Now, just like in UCB, we were computing a number called the UCB for each arm. Here, we are going to maintain what is called a belief distribution for each arm. Okay, that belief distribution is nothing but a beta distribution whose parameters are the number of successes plus 1 and the number of failures plus 1 for that arm. Okay, so I've sort of drawn the beta distribution, rotated 90 degrees over here. If you look at it like this, right, or you like this, right, so here, for example, is a beta distribution of an arm whose number of successes is as a fraction is maybe 0.7 or something like that, okay, to the total number of pulls. Doesn't seem to have very large variance, so maybe it has more pulls. This is an arm which has a similar empirical mean, but it has fewer tries, okay, and therefore it has a larger variance. But these are all beta distributions. And this beta distribution is exactly the beta distribution with parameters, the number of successes plus 1, number of failures plus 1 for that arm. Okay, this is just there. Now, what does the algorithm have to do? The algorithm has to decide which arm to pull. Okay, and how does it do that? So Thompson sampling is a genuinely randomized algorithm. Here's what it's going to do. Okay, first it does this computational step in its own mind. The agent does this, that for every arm A, you draw a sample from the corresponding belief distribution. Okay, so XTA is basically just like these are all the XTAs that I was showing you. So this is a sample drawn from a beta distribution with parameters 5 and 15, right? Now similarly, draw a beta distribution, a sample from a beta distribution with these parameters. It's a random sample, so maybe this is what you got. Okay, here this is what you got, this is what you got. These are the ones that I'm calling the X's. Okay, what is the algorithm then going to do? It has to decide which arm to pull. It is going to pull that arm which has the highest X. Okay, from your belief distribution, you're drawing samples. Whichever belief distribution gave you the highest sample, that arm you go and pull. Okay, so this is the arm here that you will go and pull. If you pull this arm, what's going to happen? It will get an additional success or a failure. So its beta distribution could change. For all the other arms, actually the beta distribution will not change. Okay, because their numbers of successes and failures will stay the same. But then again, what do? You sample, right? You draw these red dots, find which one came highest, you pull that arm. Draw red dots, find which one came highest, pull that arm. That is Thompson sampling. Okay, somebody thought about this algorithm in 1933. Okay, for a very long time, Thompson sampling was one of these algorithms that people found extremely effective in practice, but there was really no theory to back up the claim. People had not analyzed whether Thompson sampling is also actually like an optimal algorithm in the sense of having logarithmic regret and so on. That happened literally like 10-15 years back. So for about 80 years, people were using this algorithm very effectively without formally knowing whether it's a good algorithm or not. In 2011-12, okay. In fact, it's worth mentioning that the proof that Thompson sampling has logarithmic regret came out of India. Okay, so Shipra Agarwal was I don't know if she was a PhD student or postdoc at that time. She wrote this paper working with people at Microsoft Research, showing that Thompson sampling actually has logarithmic regret. That brought a lot of attention, right, from all quarters. And literally 1 or 2 years later, it was also shown that the constant, right, that accompanies the log t is optimal for Thompson sampling, just like KLUCB was. So here is an instance of, again, right, mathematics really lying at the heart of design and analysis of algorithms. For this kind of decision theory, what do you need to know? Probability. Okay. Yeah, so not surprisingly, on that same instance, the regret the Thompson sampling gives you is 463. Okay, the others were 700, 800, 1000, and so on, right? Thompson sampling is much more efficient. Questions?
Distributions or for per arm that we draw actually contribute towards pulling the optimal arm? Like, how do you interpret these distributions?
Yeah, so let's look at any of these belief distributions, okay? So what's going to happen intuitively is, early on when we do not have too many pulls for any particular distribution, it's going to have a relatively wide distribution, okay? The variance is going to be large. And so with good chance you will be getting lucky values and also unlucky values, okay? But as an arm gets pulled more and more times, its distribution will start peaking around its empirical mean, the variance will start going down. Okay, and so what will happen sort of in the limit is the arm that has the highest true mean will actually get a beta distribution which is pretty much centered around that true mean with a little bit of variance. Other arms, right, will also start getting that as they get more and more pulls. So you will mostly be exploiting, because when you draw samples from these distributions, they'll come close to true means. Unless there's an arm that has not been explored enough, which has a wide variance, which will occasionally get lucky, right, and you'll end up pulling that. And it turns out that the probabilities with which these things happen actually give Thompson sampling optimal regret.
This algorithm, was it like derived or it was just randomly assumed, let's try use it?
So unfortunately, I was not around in 1933. This paper is a relatively terse paper where it is just described in very concise terms. Frankly, I don't know how Thompson came up with this. It's not, the proof is not there, right? It's the sort of way in which he describes it also is, it's not very, you could say, negotiable by modern standards. He was not a computer scientist. In fact, the 1933 paper is from a journal called Biometrica. Okay, I have a feeling it's something related to biology. I don't know. I'm not sure. It might not be like Ramanujan, like some goddess came in his dreams or something, but it might be very different process through which the idea came into his mind.
So like, is there a more rigorous way to find out what algorithm would be best? Like, instead of randomly guessing,
How to come up with an algorithm?
to come up with an algorithm that would perform better than this.
Okay, so traditionally, at least in my time, the way people come up with algorithms is by doing it themselves. You definitely use rigor to justify your algorithm. Once you have the algorithm, right, you say that for this and this reason it is optimal in its regret, it is sort of taking so much compute, so much memory. You rationalize all that very rigorously after you come up with it. But the process of coming up with it, right, so far has been open-ended, where human beings flourish. The last 2-3 years, what has happened with generative AI, there's also ways to come up with algorithms themselves. So I don't know if you've heard, but there have been long-standing mathematical problems for which LLMs have come up with proofs, okay, recently. So there's a way of setting up a proof as a, so what is a proof really for an algorithm, right? It is a way of, for a claim or a theorem or something like that. It's a way of sequencing axioms, right, with the rules of combination, right, to build a chain all the way to the final result. So there are ways of doing this. You might have heard of matrix multiplication. It's a very sort of standard, well-known algorithm for which people knew certain complexity results. So if you do matrix so matrices, I think you should know, right? Roboticists use matrices quite a bit. So if you want to multiply two n by n matrices, if you do it the standard way, you and I write code, right? It takes order of n cubed number of steps, okay? But there's ways to bring this down, okay? There's another way to do, I think, n to the 2.7 or something like that. This number, right, has progressively been coming down. The smallest that it has come, if I'm not mistaken, is due to an algorithm that was discovered by a neural network that was trained by DeepMind precisely to do this. Okay, they set up a program that could discover new matrix multiplication algorithms, and that was able to find something which human cognition has not been able to do yet. Okay, so at least in limited spaces, you can set up machine learning to discover algorithms for you. But by and large, people have been doing it.
So like, is discovery just guessing and trying to prove why it might be better, or?
Well, humans tend to get better with time, right? It's not guessing. It might be some amount of guessing, but your collected experience and knowledge, right, maybe like guides you, right, in a certain way, and
No,
you're a little
I'm
bit more
saying-
efficient with it.
I'm saying for the LLM that they trained, like, how did they train the LLM to approach the problem?
It is trained, it is given a lot of exposure to smaller variants of the problem. So maybe for small matrices, right, you kind of brute force and you know what's the right way to do it. It sees a lot of those patterns, and from that, right, it sort of discovers a general thing which humans maybe are not able to do. It also does some reinforcement. This is actually based on reinforcement learning. So what I said is only approximately true.
The distribution he is using here is a
Beta distribution.
beta distribution. Will it be the same if he uses a Gaussian distribution? Or
Great question. Okay, so you're the ideal student to be doing probability if you've not already done it, because the reason we are using a beta distribution is there is this connection between a beta distribution and a Bernoulli reward distribution. See, our rewards are 0 and 1, right, coming from a Bernoulli. So if you apply something called Bayes' theorem, the formally correct way to refine your beliefs when you're getting Bernoulli data is to keep a beta distribution. If your rewards internally were Gaussians, let us say, instead of heads and tails, you were actually getting like real valued rewards which were Gaussian, you would have to keep Gaussian beliefs over those. So there's this thing called a conjugate prior. There are these families of distributions which are the ways to implement Bayes' theorem depending on your input reward distribution. Yeah, so the gist is that Thompson sampling also does extremely well in practice. It's also been shown to be optimal. It gets 463. So let me give you consolidated results. Again, to reinforce the point that, see, we started with epsilon greedy. It had this parameter epsilon which we had to tune, right? It was, I don't know, not doing so well on some problem instances. We then progressed to UCB, which got optimal dependence on the horizon, and then to KL, UCB, and Thomson, which are not only optimal in terms of the log t dependence, even the constant is better, and that theory translates into practice, okay? So at 10 to the 5, which is what I've shown you so far, the regrets are 800, 1100, 700, 400. But then look at this, okay? This is a plot of regret of these 4 algorithms as the horizon is varied, okay? So epsilon greedy, although it did beat, I think, UCB at, so epsilon greedy is pink, okay? It did better than UCB, which is green, okay, at 10 to the 5. But when you go to 10 to the 6, okay, the epsilon greedy again goes off the rails. Okay, maybe you have to tune it differently to get a better number here, but if you do that, it won't do so well here. There are all these issues, right? On the other hand, you notice that this is actually a graph plotted on a logarithmic scale. So what have I done? 10 to the 2, 3, 4, 5, 6. It's multiplied by a factor of 10, right, for each increment. You see that these 3 graphs, UCB, KL, UCB, Thomson sampling, are all kind of becoming like straight lines. That's what you should expect, right? We said that the regret is about log t. If regret is log t and we're plotting it on log scale, it has to be linear, right? You see that happening, okay? So Thomson sampling really in the last 15 years has emerged as the method of choice for all bandit problems. People use it very extensively. So if you're scrolling and somebody showed you an ad or showed you an article to read, somebody might have used Thomson sampling behind the scenes, right, to determine that that's what they should be showing you. Okay, so probability is happening everywhere, right? Wherever AI is, right, recommender systems are, and so on. There is this kind of reasoning that happens, and many of these algorithms are what are called algorithms implementing the principle of optimism in the phase of uncertainty. So if you look at UCB, right, what did we do? For each arm, we gave it an additional exploration bonus. So when we don't have full information about an arm, we add the bonus, right? We are optimistic that, right, the empirical mean, if it is here, the true mean will actually be higher than that, right? We give it that advantage. Similarly, in Thomson sampling, what did we do? We sampled from these belief distributions and we went the one with the highest sample, right? So we are hopeful that when we don't know about something, that it is its best, right, rather than it is its worst. And optimism in the face of uncertainties tends to be a good practice, right, wherever we have to do regret minimization. Okay, all right, so let me conclude. So we've studied a very, you could say, simplified setup of bandits. in practice, applications can stretch it in multiple different ways. You don't always need to have the same set of arms. Ads, for example, will keep coming in and going out, okay? So you might have to keep adapting to newer data. You won't get rewards immediately. So even with ads, right? Once you show somebody an ad, right? They click, that data goes to some server, it goes somewhere else. It might come back to the decision maker only like a few hours later, right? So delayed rewards is a very practical constraint sometimes. These arms might not all be independent, right? They might have some structure which lets us generalize whatever we've learned from one arm to another arm. So contextual bandits is yet another formalism that I've not really gotten into over here. The rewards themselves could change over time, okay? We assume that the probabilities with which you'll get 0 and 1 for each arm will stay fixed. But in practice, that could also change. So if they are drifting slowly, right, can we do something about it? We can, okay? So those are called non-stationary bandits. So what really I have communicated is like a basic heart of way to reason about bandits. But in practice, you might have to make some accommodations for practical constraints such as this, okay? Okay, what is the whole summary of bandits? This is literally the one talk I'm doing with you on bandits. So how should you remember it? So this is designed, right, for agents to interact with systems which are unknown, okay, and what they have is a decision to make among a few different possible options. When they exercise an option, they get stochastic feedback. They get like noisy feedback. They still have to learn something based on that. This is a classical problem. It's been studied, as you saw, for almost 100 years. It is an instance of a problem where theoretical advance, right, has really become the underpinning of thinking about the problem, designing analysis, designing algorithms, and so on. And good theory often translates into good practice. It's not always true everywhere, right? Bandits is one setup in which that happens. Okay. All right. So if you want to follow up, this is also, I think, good reference for you. There's a very classical textbook on reinforcement learning by Sutton and Bartow, which is actually what most reinforcement learning courses will use as their textbook. So the second chapter in Sutton and Bartow is about bandits. That will give you a very sort of nice, intuitive sort of flavor about how things work. Thompson sampling in particular, some of you have asked questions. Here's a relatively accessible article. Okay, so now's the time to invest the effort to learn many of these topics. Okay, so in the long term, it will definitely help if you do that. Okay, all right, thanks.
So I'm Nilesh Astukar. I'm a second year CSE student, and I just attended this lecture by Professor Shivaram sir. The lecture was really great. It encompassed entirety of the introduction of probability and also various distribution. We also went through a lot of different samplings such as epsilon greedy, UCB, KLUCB, and he also introduced us to various technical terms such as what's regret, and along with that, finally we went on to Thompson sampling, and he also concluded how that was like the best one. We also compared different sampling methods with the number of iterations of the data that had been done and how it affected the performance or the regret score of different sampling methods. Eventually, with Thompson sampling being being one of the best ones, the lecture was really interactive as he interacted throughout with the students. There were also initial experiments such as coin toss experiments, which really engaged our attention and helped us understand the importance of such sampling methods and probability in real life.